Welcome to this explainer. Today, we're taking a trip into the innermost, most extreme reaches of our solar system. We're going to explore a really captivating journey, starting from a massive historical astronomical blunder, all the way to the cutting-edge technology that is literally skimming the surface of our sun right now. The way we understand this chaotic, fiery region has completely transformed over the last century and a half, and it's a fantastic story. So get this, for centuries, some of the absolute brilliant minds in astronomy were dead set on the idea that another whole world was hiding right there in the solar glare, just out of our reach. But its ultimate fate is this incredible plot twist that fundamentally changed physics as we know it. Let's dig into exactly what happened to this elusive, missing world. Section 1. The Phantom Planet Vulcan. Picture the 1850s. Newtonian physics was the undisputed king of science, but there was this one maddening glitch, a tiny 43 arcsecond anomaly in Mercury's orbit that Newton's laws just couldn't explain. Enter the mathematician Urbain Le Verrier. This is the guy who famously predicted Neptune's existence, so people trusted him. He postulated that the gravitational pull from an undiscovered planet, which he named Vulcan, was the culprit. That kicked off a massive, decades-long hunt. During the total solar eclipses of 1869 and 1878, astronomers like James Watson were so eager that they actually claimed to have seen it. But it was an illusion. Wishful thinking, really. Finally, in 1908, after running comprehensive photographic observations, the Lick Observatory definitively closed the case. They had proof. There was no Vulcan. Section 2. Einstein solves the mystery. In 1915, Albert Einstein stepped in. And he didn't just cross Vulcan off the map, his theory of general relativity entirely rewrote the rules of gravity. See, Einstein proved that the sun's massive bulk actually curves the very fabric of spacetime around it. Mercury's strange little orbital wobble wasn't being caused by some hidden planet tugging on it, it was simply following the natural warped curvature of space. Vulcan was finally laid to rest, but the hunt for its ghost had pushed human knowledge forward in a massive way. Section 3. The Hunt for Vulcanoids. After Vulcan was debunked, astronomers pivoted. They started searching for something called Vulcanoids. Hypothetically, these are a population of tiny, ancient asteroids surviving in a dynamically stable, super narrow band, just 0.16 to 0.18 astronomical units from the Sun. If they exist, these rocks would be untouched primordial remnants of the very early solar system. To put that distance into perspective, 0.16 astronomical units is a mere fraction of the distance between Earth and the Sun. So we're talking about theoretical rocks orbiting perilously close to a giant raging inferno. And we have looked everywhere for them. Despite pointing our most advanced, sensitive instruments right into the inner solar system, we haven't found a single rock. Teams used coronagraphs on the SHO spacecraft, they used the Messenger probe during its closest passes by Mercury, and they even ran high-altitude flights by the Southwest Research Institute and NASA Dryden. The Stereo spacecraft actually used occulting disks to block out the sun's blinding glare, and that provided a definitive limit. They proved with absolute confidence that there are no Vulcanoids larger than 5.7 kilometers in diameter out there. Zero. So if any exist at all, they have to be incredibly, incredibly small. Section 4. Physics of the Inner System. Now, why is it so empty out there? Well, astrophysical math shows us exactly how intense the physical forces are near a radiating sphere like our sun. Research, like this foundational 1962 paper by Arnold Guess, proves that when a particle orbits that close to a massive radiation source, the drag forces increase dramatically compared to what you'd expect from just a simple point of light. It is a wildly hostile environment. And that builds into an incredible, real-world phenomenon known as the Poynting-Robertson effect. Basically, because a small particle absorbs and re-emits solar energy while moving forward in its orbit, it acts almost like running headfirst into a heavy rainstorm. The radiation literally pushes back against its forward motion, causing it to lose momentum. Over time, this effect sweeps the inner solar system completely clean of dust and tiny particles, dragging them inward to a fiery demise. This is likely exactly why we don't see small Vulcanoids. They were swept into the sun a long, long time ago. Section 5. Parker's solar probe dives in. 430,000 miles per hour. That is roughly 0.064% the speed of light, and it is the top speed of the Parker solar probe. It is the fastest object ever built by humanity, period. Through a complex series of Venus gravity assists, Parker is dropping into this highly eccentric orbit that will eventually skim within just 9.86 solar radii of the sun's center. We are touching the sun, folks. Shielded from brutal 2,500-degree Fahrenheit temperatures by a state-of-the-art heat shield, Parker's instruments are rewriting textbooks right now, showing us exactly how solar wind gets its energy. The probe's Whisper imager is out there specifically looking for that hypothetical dust-free zone created by the forces we just talked about. Meanwhile, the field suite uses these 2-meter-long antennas made of a highly resilient niobium alloy. Get this, those antennas project completely unprotected directly into the harsh sunlight, capturing the scale and shape of the electric and magnetic fields in the solar wind at a mind-boggling rate of 2 million times per second. Section 6. Bepi-Colombo's Journey to Mercury. Let's move slightly further out to the sheer ingenuity of the Bepi-Colombo mission. This is a joint European and Japanese endeavor, and what's so cool about it is that it's actually multiple spacecraft literally stacked into one, designed to separate right when they arrive. The ESA-led transfer module does the heavy lifting to get them there. Then they split. The ESA-led planetary orbiter will map Mercury's surface and investigate its bizarrely large core, while the JAXA-led magnetospheric orbiter, which they named MEO, studies Mercury's magnetic field. By splitting up like that, they get unparalleled complementary measurements from two completely different locations at the exact same time. Now, actually getting a spacecraft to orbit Mercury is notoriously unbelievably difficult. The sun's gravitational pull is just immense. You can't just point a rocket straight there. You'd accelerate way too much and fly right past the planet. So it requires an exhaustively precise sequence of 9 complex gravity assist flybys over an 8-year journey. Bepi-Colombo launched way back in October 2018. It already used its Earth flyby to test onboard instruments, like the Italian spring accelerometer, then swung past Venus twice, and is doing 6 flybys of Mercury itself before finally hitting the brakes for orbital insertion in late 2026. Ultimately, Bepi-Colombo is out there to answer some monumental questions for us. How does a planet sitting so close to the sun, where surface temps regularly hit 800 degrees Fahrenheit, manage to harbor water ice in its shadowed polar craters? Why is its core so disproportionately massive? And incredibly, the mission is going to perform even further tests on Einstein's theory of general relativity right there on site. By unraveling Mercury's most stubborn mysteries, this mission isn't just going to teach us about one weird little rock. It's going to fundamentally reshape our understanding of how our entire solar system formed. So, from the phantom planet Vulcan that totally forced us to rethink gravity, to the elusive Vulcanoids we're still keeping an eye out for, this inner region of space is just a masterclass in cosmic mysteries. As the Parker Solar Probe and Bepi-Colombo press on with their daring, high-stakes missions, it leaves us with one really exciting thought. What other invisible truths are just waiting to be illuminated in the intense, fiery glare of our local star?